Welcome to the Deep Dive. We plunge into fascinating topics to bring you, well, the most important insights and those key aha moments.
Exactly.
Today we're looking up, way up, into our cosmic neighborhood. It's captivating, sometimes mysterious, maybe even a little bit threatening sometimes.
That's right. I mean, think about it from those beautiful comets we sometimes see to objects we don't see that could pose a risk, and even, visitors from totally different star systems. Space is busy.
It really is. Dynamic, crowded. We're learning more all the time about what's zipping past. So our mission today, using these great sources you pulled together, is to kind of unravel the secrets of these celestial wanderers.
Yeah, get into what they are, what they could mean for us here on Earth.
And what we're doing about it, humanity's efforts to understand, maybe even defend against them. We really want to pull out the key stuff, give you those aha moments, and show you why it matters.
So we'll start with comets, those dirty snowballs, then shift over to near-Earth objects, the NEOs, and the whole planetary defense angle. And then the really mind-bending part. The confirmed interstellar visitors. Things from outside our solar system. We've got material from the Lunar and Planetary Institute, crucial reports from ESA and NASA on defense, and some cutting-edge research on those interstellar objects.
Sounds like quite a journey. So let's start with the familiar, maybe, comets. We all picture them, that streak of light. But what are they really?
Well, the classic description, dirty snowballs, is actually pretty spot on. They're essentially leftovers from when the solar system first formed.
Leftovers. Like cosmic scraps.
Kind of. Remnants of that primordial solar nebula, basically chunks of ice, dust, frozen gases all packed together. They've been kept in deep freeze for billions of years, way out there.
Way out where, exactly?
Mostly in two main regions. There's the Kuiper Belt, which is, out beyond Neptune and Pluto.
Okay.
And then even further out, there's this vast spherical cloud of them called the Oort cloud. Really, really far away.
So like time capsules from the dawn of the solar system. What secrets can they tell scientists?
Exactly. Relics from the earliest times. They hold vital clues about our origins. I mean, some scientists even think comets might have delivered water to the early Earth.
Really? Water?
Yeah, it's a leading theory. And there are even studies looking at possible water ice deposits, say, in permanently shadowed craters on the moon that might be from unfortunate comet impacts. It hints at how fundamental they could have been.
Wow. Okay, but when we see them, they're not just icy lumps, are they? They have those amazing tails. How does that happen? What's the anatomy?
Right. So at the heart is the solid nucleus. That's your dirty snowball, ice, dust, rock, frozen gases.
Got it.
As it gets closer to the sun, the heat starts to work on it. The ice is vaporized, they turn straight into gas, and this gas, along with dust particles dragged along with it, flows away from the nucleus.
And that forms?
That forms the coma. It's this huge, fuzzy cloud of gas and dust around the nucleus. And when I say huge, I mean it. A coma can be millions of kilometers across. Bigger than Earth sometimes, though obviously incredibly thin.
Millions of kilometers. And that leads to the tails we see. The sunlight must be key there.
Absolutely key. Sunlight does two things. It illuminates the dust particles, making them visible, and it ionizes the gas, strips electrons off, causing it to glow, often blue.
So it's not just one tail.
Usually not. You typically get twin tails. There's the ion tail or gas tail. That's the glowing blue one I mentioned. It's made of charged particles, so the solar wind, this stream of particles constantly flowing from the sun, pushes it directly away from the sun. Always.
Directly away. Okay. And the other one?
The other is the dust tail. This one's made of slightly larger particles, like smoke-sized dust. It's pushed by the pressure of sunlight itself, solar photons. It tends to be broader, maybe yellowish or white, and often curved, slightly kind of lagging behind the comet in its orbit.
So Isaac Newton, way back, he figured sunlight was pushing things away somehow. That's amazing.
He did. He talked about a repulsive force from the sun. Incredible intuition. And these tails, they can be mind-bogglingly long.
How long are we talking?
Up to 150 million kilometers. That's the same distance as the Earth is from the sun. An astronomical unit.
Just staggering scale. And sometimes bits of this stuff fall off and reach Earth, right? That's meteor showers.
Precisely. As comets swing close to the sun, they shed debris dust, pebbles, little bits of ice along their path. When Earth's orbit intersects with one of these debris trails,
we fly right through it.
We fly right through it. And those tiny particles hit our atmosphere at high speed and burn up, creating those streaks of light we call shooting stars or meteor showers.
Like the Perseids in August.
Exactly. The Perseids come from Comet Swift-Tuttle. Or the Leonids in November, they're from Comet Tempel-Tuttle. Little gifts from comets.
Now, these comets, they have regular paths, don't they? They're not just wandering randomly. Some are famous for coming back.
That's right. They follow elliptical orbits around the sun. We group them into short-period comets, those taking less than 200 years to orbit.
Like Halley's.
Like Halley's, yes. And long-period comets, which take more than 200 years, sometimes thousands or even millions of years.
Okay, let's talk about Halley's. It's probably the most famous one. What's its story?
Halley's is iconic. So back in 1705, Edmund Halley was studying records of comets seen in 1531, 1607, and 1682 using Newton's brand new laws of motion.
Which were revolutionary at the time.
Totally. Halley realized these might actually be the same comet returning. He predicted it would come back again in 1758.
And did it?
It did, right on schedule. Sadly, Halley himself didn't live to see it, but they named it in his honor. It was this huge confirmation of Newton's physics, showing we could predict the heavens.
What a legacy. And it's been seen throughout history, right?
Right.
Are there other, maybe less predictable interactions between comets and planets?
Oh, yeah. Halley's average period is about 76 years, but it varies a bit because planets, especially big ones like Jupiter, tug on it gravitationally.
Gravity's influence.
Exactly. Planetary gravity can seriously mess with a comet's orbit. It can nudge it onto a different path, capture it into orbit around the planet, or even cause a direct impact.
An impact? Has that happened?
Famously, yes. In 1994, the Hubble Space Telescope watched as fragments of Comet Shoemaker-Levy 9 slammed into Jupiter, one after another.
I remember seeing those images. Huge, dark scars on Jupiter.
Yeah, it was a dramatic wake-up call, really. Showed these impacts happen, even now.
From science to history, comets used to be seen very differently, didn't they? As omens, signs from the gods.
Oh, absolutely. For most of human history, they were awe-inspiring, often terrifying, seen as heralds of disaster, war, the death of kings, or sometimes good fortune.
Any specific examples?
Plenty. We know the Chinese were keeping records of Halley's Comet way back, at least to 240 BC. Think about that.
Incredible continuity.
And maybe the most famous depiction is on the Bayeux Tapestry, showing Halley's Comet appearing before the Norman conquest of England in 1066. William the Conqueror supposedly took it as a good omen for his invasion.
Wow. Talk about high-stakes interpretation. Any other famous figures linked to comets?
Oh, loads of legends. Hannibal supposedly killed himself after hearing a comet foretold his doom. Charlemagne was crowned when one appeared, then apparently saw another one shortly before he died 14 years later and took it as a warning.
And Napoleon. Didn't he ignore one?
The story goes he laughed off a comet seen before Waterloo as a bad omen. Maybe shouldn't have.
And then there's Mark Twain. What's that connection?
Ah, that's a great one. Twain was born in 1835 when Halley's Comet was visible. He apparently joked he came in with the comet and would go out with it.
And maybe.
He died in 1910, the very next time Halley's returned. It's probably apocryphal, but it's a fantastic story, right? Shows how these things weave into our culture.
It really does. From folklore to actually sending spacecraft to these comets, that's a huge leap. What did missions like Giotto teach us?
A massive leap.
Yeah.
Giotto, the European Space Agency mission, flew by Halley's in 1986. Got the first ever close-up pictures of a comet nucleus just 500 kilometers away.
What did it see?
It saw this dark, irregular lump spewing jets of gas and dust. It detected water, organic molecules, confirmed the dirty snowball idea, but showed it was more complex, darker than expected. It even survived the flyby, despite taking some hits from dust, and went on to visit another comet later.
And NASA got involved too, right? Stardust?
Yeah, Stardust was amazing. Launched in 1999, flew through the coma of Comet Wild 2 in 2004, actually collected dust samples.
Collected them and brought them back.
And brought them back to Earth in 2006 for scientists to study in labs. That was huge. Found amino acids, glycine, building blocks of life.
Incredible. So these missions really changed the game.
Completely. Deep Space One also flew by Comet Borley, got great data. And then Rosetta. Wow.
What did Rosetta do?
ESA's Rosetta, launched 2003, didn't just fly by. It went into orbit around Comet 67 Pichuryov-Gerasimenko in 2014, studied it for almost 2 years.
Orbited a comet.
Orbited it, mapped it, watched it change as it approached the sun, and it even deployed a lander, Philae, onto the surface.
Landed on a comet. That's sci-fi stuff.
It really was. These missions gave us this intimate portrait of comets as dynamic, evolving worlds full of clues about the early solar system and maybe even the origins of life.
Okay, so comets are fascinating, scientifically vital. But sometimes things hitting planets isn't just theoretical, like Shoemaker-Levy 9. That brings us to, well, the less pretty side. Planetary defense. Near-Earth objects. NEOs.
Right. Let's shift gears. NEOs, near-Earth objects, broadly, that's any asteroid or comet whose orbit brings it relatively close to Earth's orbit, specifically within about 1 1/3 times Earth's distance from the sun.
So in our general neighborhood.
In the neighborhood. Now, within that group, there's a subset we watch very closely. PHOs,
Right.
potentially hazardous objects.
Actually hazardous. Okay, what makes them potentially hazardous?
Two things. Their orbit has to bring them within about 4.7 million miles, or 7.5 million kilometers of Earth's orbit. It's pretty close, astronomically speaking.
Right.
And they have to be big enough to cause significant damage if they did hit. The threshold is generally considered to be about 140 meters, roughly 460 feet, across or larger.
140 meters. How bad would an impact from something that size be? Can you give us a sense of the scale of the hazard?
Yeah, let's break down the hazard by the numbers. Something small, say 10 meters, about 30 feet across. We probably get one of those entering the atmosphere every decade or so.
What happens?
Big fireball, really bright, strong sonic boom. Might shatter some windows, like the Chelyabinsk event in Russia in 2013. Scary, but generally not devastating.
Okay, what about bigger, say 50 meters, like maybe the Tunguska event size?
Right, around 50 meters, maybe once every 1,000 years on average. That could cause local devastation. Flatten forests over a huge area like Tunguska, or if it hit a populated area, it could destroy a city. Serious regional effects.
Okay, that's significant. Now that 140-meter PHO threshold.
Yeah, 140 meters. Estimated impact frequency maybe once every 20,000 years. That creates a crater maybe 1-2 kilometers across. It would be deadly over a metropolitan area, maybe even a small state. We're talking mass casualties.
Grim stuff. And bigger still.
Go up to a kilometer, about 0.6 miles across. Impact maybe every 700,000 years. That's a 10-kilometer crater. Global climate effects, widespread devastation, possible collapse of civilization territory.
And the dinosaur killer size.
Oh, it was likely around 10 kilometers, maybe 6 miles across frequency, maybe once every 100 million years. Creates a 100-kilometer crater, global catastrophe, mass extinctions, like fundamentally changing life on Earth.
Puts it in perspective. So how good are we at finding these things?
Yeah.
Especially the ones like 140 meters or bigger that could cause regional disaster.
Well, the good news is, for the really big ones, the kilometer-plus civilization enders, we think we found about 95% of the NEO population.
And none of those are a threat right now.
Correct. None of the known ones pose a significant impact threat for the foreseeable future. But as you get smaller, our completeness drops off sharply.
How sharply?
For the 140-meter objects, we've probably only found less than half. Maybe 40–50%. For 50-meter objects, it's maybe less than 8%, and for the 10-meter ones, less than 1%.
So there are potentially tens of thousands, maybe hundreds of thousands, of potentially hazardous objects out there we haven't even spotted yet.
That's the challenge, yes. They're numerous, they're often dark, and they move fast. Finding them all is a huge task.
Which is where NASA's Planetary Defense Coordination Office comes in, right? What's their role?
Exactly. NASA has a mandate from Congress, from the 2005 NEO Survey Act, to find, track, catalog, and characterize these objects. The PDCO, the Planetary Defense Coordination Office, was formalized in 2016 to lead and coordinate all of NASA's planetary defense efforts.
So they're the central hub. What does their strategy involve? It's not just finding them, is it?
No, it's a whole pipeline. First, find, detect, and track NEOs. Second, characterize. Figure out their size, shape, rotation, composition, what are they made of. That's crucial for planning any mitigation.
Okay. Find, characterize.
Third, warn. If a potential impact is detected, provide timely and accurate warnings to government agencies, the public, internationally. Fourth, plan. Develop strategies and technologies for mitigation. How would we stop an impact?
And finally,
mitigate. If necessary, coordinate and carry out a response mission, like deflecting or disrupting the object. It's a comprehensive approach.
and we've actually tested that last part, haven't we? The DART mission.
Yeah.
That felt like a huge moment.
It was a huge moment. DART, the Double Asteroid Redirection Test, launched in 2021, impacted in 2022. It was the world's first test of kinetic impactor technology.
Kinetic impactor meaning basically hitting it with a spacecraft.
Pretty much. Slamming a projectile into the asteroid to nudge its orbit. DART targeted Dimorphos, a small moonlet orbiting a larger asteroid called Didymos, about 7 million miles away.
And did it work? Did it nudge it?
It worked beautifully. The impact changed Dimorphos' orbital period around Didymos by 32 minutes. That was way more successful than the minimum requirement, about a 5% change in its orbital speed.
So we proved we can move an asteroid.
We proved the concept, yes. We hit a small target far away, and we measurably changed its path. It was a massive proof of principle for planetary defense.
And that involved international partners, too.
Absolutely. Italy provided a small CubeSat called LISA-Cube that flew nearby and imaged the impact and the resulting plume. And telescopes all over the world, on every continent, observed the aftermath. Plus, ESA, the European Space Agency, is sending a follow-up mission called Hera.
Hera. What will that do?
Hera will launch maybe as early as 2024, get to Didymos and Dimorphos later in the decade, and study the impact crater DART made, measure Dimorphos's mass precisely, and really analyze the effects of the impact in detail. It's crucial follow-up science.
So DART tested the mitigate part. What about the find part? How are we getting better at discovering these NEOs?
That's where new survey capabilities come in. The big one is the NEO Surveyor mission.
NEO Surveyor, what is it?
It's a space-based telescope designed specifically to hunt for NEOs using infrared light. It's planned to launch no later than 2028.
Why space-based? And why infrared?
Space gets you above Earth's atmosphere, which blocks a lot of infrared. And infrared is great because asteroids absorb sunlight and re-radiate it as heat, as infrared light. So even dark asteroids glow in the infrared, making them easier to spot, especially against the cold background of space.
Makes sense. What's the goal for AO Surveyor?
The goal is ambitious. Within about a decade of launch, it aims to find over 90% of the NEOs larger than 140 meters, those potentially hazardous ones. That would roughly triple our current catalog for that size range.
That would be a huge leap in our awareness. And they're ground-based surveys, too.
Oh, yes. Programs like the Catalina Sky Survey, CSS, Pan-STARRS in Hawaii, Ablato CS, Asteroid Terrestrial Impact Last Alert System. These are constantly scanning the sky every clear night. They're our frontline right now. And facilities like the Goldstone Solar System Radar can ping asteroids with radio waves to get incredibly precise orbit data and even images.
It sounds like a global network is really needed.
It absolutely is. An impact threat is a global problem, not just one country's issue. That's why international cooperation is so vital.
How does that work in practice?
There are key international bodies. The International Asteroid Warning Network, IAWN, coordinates observations and warnings among observatories worldwide. NASA helps coordinate it. It has like 50 signatories from 20 countries now.
Okay, IAWN for warning. What about planning a response?
That's where SMPAG comes in the Space Mission Planning Advisory Group. It brings space agencies together to discuss technologies and strategies for actually deflecting an asteroid if needed. Both IAWN and SMPAG were endorsed by the UN, which shows the level of international buy-in.
Yeah, it's good to know there's that level of coordination. And speaking of global focus, there's a specific asteroid causing a buzz for 2029, isn't there? Apophis.
Ah, yes, 99942, Apophis. This is going to be really special. On April 13th, 2029, Apophis is predicted to fly extremely close to Earth.
How close? Dangerously close.
Not dangerous, we're certain of that now, but incredibly close. It will pass within the altitude of our geostationary satellites, about 31,000 kilometers, or 19,000 miles above the surface.
Wow, that is close. Closer than the moon, obviously.
Much closer. So close that for several hours it will be visible to the naked eye from large parts of the Eastern Hemisphere, Europe, Africa, Asia, like a star moving steadily across the sky.
Visible with the naked eye. An asteroid.
Yes. It's an absolutely unprecedented opportunity for science and just for public awareness. A once-in-a-lifetime event, really.
And this is why the UN is proposing 2029 as the International Year of Planetary Defense.
Precisely. IYPD 2029. The Apophis flyby is the perfect anchor for it. The goals are broad. Raise global awareness about asteroids and comets, promote the importance of planetary defense.
Sort of demystify it, maybe debunk some myths.
Exactly. Debunk misinformation about impacts, stimulate interest in space, especially among young people, and really highlight how nations working together is essential for protecting the planet. It's a great opportunity.
It really sounds like it. Okay, so we've covered comets, our solar system neighbors, and NEOs, the potential threats. But now let's go further out to visitors from other star systems entirely. Interstellar objects.
Right. This is a relatively new, super exciting field. Interstellar objects, or ISOs, are basically any object, asteroid, comet, maybe even a rogue planet that's just passing through our solar system. It's not gravitationally bound to our sun. It comes in from interstellar space, loops around the sun maybe, and heads back out.
So they're like cosmic tourists. Where do they come from? How do they get loose?
They get ejected from their own home star systems. Could happen in lots of ways. Maybe strong gravitational kicks from giant planets like Jupiter tossing things out.
Okay.
Or complex orbital dynamics and systems with multiple stars, binary stars, for example. Or maybe even huge events like supernova explosions could send debris flying. Once they're ejected, they just wander the galaxy.
Wander the galaxy. For how long?
Potentially for millions, even billions of years, drifting through the void until they happen to pass through another star system like ours.
That's mind-boggling. Are they rare visitors, or are there more than we think?
Well, detecting them is hard. They're usually small, dark, and moving incredibly fast relative to us. But based on the ones we have seen, astronomers now estimate that probably several ISOs pass inside Earth's orbit every single year.
Several per year.
And maybe 10,000 are passing inside Neptune's orbit at any given moment. The galaxy might be littered with these things. We just couldn't see them until recently.
So which was the first one we actually confirmed, the one that really kicked off this field?
That was Oumuamua, discovered in October 2017 by the Pan-STARRS Survey telescope in Hawaii.
Oumuamua, great name. What does it mean?
It's Hawaiian for a messenger from afar arriving first, or scout. Very fitting.
Perfect. And what made it so weird and interesting?
Oh, several things. First, its trajectory was strongly hyperbolic. It was clearly coming in way too fast to be bound to our sun. That confirmed its interstellar origin.
Okay, so definitely from out there. What else?
It showed this slight non-gravitational acceleration, meaning something other than the sun's gravity was pushing it slightly. Usually for comets, that's outgassing ice turning to gas, acting like tiny rockets.
But Oumuamua didn't look like a comet.
No, it didn't have a visible coma or tail, no signs of gas or dust. So what was pushing it? That sparked a lot of debate.
What were the theories?
Most scientists favor natural explanations. Maybe it was releasing gases we couldn't easily detect. Maybe it was made of something unusual, like solid nitrogen ice that vaporized differently. Or maybe its shape played a role. It seemed to be very elongated, maybe tumbling. Some even proposed it could be a thin solar sail of extraterrestrial origin, though that's highly speculative.
Wow. Okay, so lots of mystery there. Any other weird things about it?
It had this unusually high reflectivity, and it came from the direction our solar system is moving through the galaxy, the solar apex. Just odd. It also set a record for the highest eccentricity, how stretched out its orbit was, at 1.199. Anything over 1 is unbound.
So Oumuamua was the first messenger. Who came next?
The second confirmed ISO was 2I Borisov, discovered in August 2019 by an amateur astronomer, Gennady Borisov.
Borisov. Was it as weird as Oumuamua?
Actually, no. Borisov looked much more like a conventional comet, just one on an interstellar trajectory. It had a coma, a tail. Observations showed its composition wasn't wildly different from comets in our own Oort cloud. It even started to break apart a bit later, which comets sometimes do.
So one weird one more normal one. Have there been others?
Yes. Just recently, we got 3I Atlas, discovered by the ATLA survey system. This one's notable because it smashed Oumuamua's record for eccentricity. It's way up at 6.1.
6.11. That's really moving.
Oh, yeah. Its interstellar velocity is around 58 kilometers per second. That's fast. It'll make its closest approach to the sun in October 2025. Each new discovery adds another piece to the puzzle.
It really does. Now, besides these bigger objects, what about smaller stuff, like interstellar meteors hitting Earth? Is that a thing?
There's research into that, yes. Trying to identify meteors recorded entering our atmosphere that had trajectories suggesting they came from interstellar space.
Any candidates?
There are a couple of prominent candidates, one from 2014 near Papua New Guinea, another from 2017. The 2014 one especially got attention because analysis suggested it hit with very high speed, around 60 kilometers relative to the sun. The U.S. Space Command even confirmed the velocity data seemed accurate.
So, interstellar meteor confirmed.
Well, it's debated. Some astronomers are skeptical, pointing out that measuring meteor speeds that precisely is really tough, and small errors could make a bound object look unbound. There were also claims about retrieving fragments from the 2014 event, but those claims have been met with considerable skepticism from the scientific community, too.
So it's tricky to be sure about the smaller ones.
Very tricky. You need incredibly precise measurements to distinguish a truly hyperbolic interstellar trajectory from just a highly elliptical, near-parabolic one from our own Oort cloud. And just finding these faint, fast meteors is hard enough.
It sounds like better telescopes are key to making progress here.
Absolutely, and that's what's coming. We're entering a new era of discovery thanks to next-generation sky surveys.
Like which one?
The big one is the Vera C. Rubin Observatory, currently being built in Chile. Used to be called LSST. When it comes online, hopefully soon, it will scan the entire southern sky every few nights with unprecedented depth and speed.
What will that mean for ISOs?
It's expected to find many more interstellar objects, maybe several per year or even more. We'll finally start to build up a real sample size, understand how common they are, what they're typically like.
And are we planning missions to actually visit one of these interstellar objects?
There are concepts and even missions in development. ESA's Comet Interceptor mission, set to launch around 2029, is really cool.
Comet Interceptor, how does that work?
It's designed to go into space and basically, it'll park at a stable point, the Sun-Earth L2 Lagrange point. Then, when a suitable target is found, ideally a pristine long-period comet, or, even better, an interstellar object heading into the inner solar system, Comet Interceptor will be dispatched to fly by it.
So it's ready to go, waiting for a target of opportunity.
Exactly. It's a rapid response mission. It even has 3 spacecraft that will separate to study the object from multiple viewpoints simultaneously.
That sounds incredibly smart. Any other ideas? Like chasing Oumuamua?
There are conceptual studies, like Project Lyra. The idea is to figure out how we could send a probe to catch up with a fast-moving ISO, like Oumuamua, maybe using advanced propulsion like solar sails or gravity assists. It's challenging because they're moving so fast, but people are thinking about it.
So looking ahead, what do you expect? More discoveries, maybe samples.
Definitely more discoveries, maybe a steady stream every few years thanks to Rubin Observatory. We'll get better at classifying them, understanding their origins. Maybe eventually, yes, sample return missions, though that's a huge technical leap. But ultimately, studying these visitors will teach us so much about planet formation everywhere.
How so?
By seeing what kind of stuff gets ejected from other star systems, we learn about the building blocks and processes happening around other stars. It may even reshape our understanding of the universe and our place in it. Are solar systems like ours common? Rare? What varieties out there? These interstellar messengers carry clues.
It really brings it all together, doesn't it? From seeing comets as omens.
Right, like on the Bayeux Tapestry.
To understanding their chemistry, using that knowledge to defend our planet, and now reaching out to understand objects from entirely different stars. It's an incredible arc of human curiosity and capability.
It really is. And that knowledge connects everything. Understanding comets helps us understand INEOs. Understanding both helps us put these interstellar visitors into context. They're all pieces of the same cosmic puzzle, how planetary systems form and evolve.
And this deep dive really shows, I think, how this isn't just abstract astronomy. It connects directly back to us here on Earth. From enjoying a meteor shower.
Yeah, those little bits of comet dust.
To the very real need for global cooperation on planetary defense. We're not just passive observers anymore, are we?
Not at all. We're actively engaging. We're sending probes, we're building shields, we're scanning the skies with ever more powerful eyes. It's a fundamental shift.
And as we keep looking out, sending probes, building these incredible instruments, we're learning as much about ourselves, maybe, as we are about space.
I think that's true. We're learning about the origins of our own world, seeing if the processes here are universal, and we're seeing what humanity can achieve when we combine scientific discovery, technological innovation, and crucially, international collaboration to face these big universal challenges.
So, a final thought to leave you with. As we anticipate the next Oumuamua or Borisov, what new secrets might that next interstellar visitor unlock? What might it tell us, not just about the vast universe out there, but maybe something profound about us, too?